Imagine this. You go to the doctor's office, and they tell you that you need a shot. But then, they let you choose between two different syringes. Which one would you pick? Left or right? Both of them hold the same dose, so does the choice even matter? The answer is yes. There is a difference, and it all has to do with a difference in sensitivity. How much the output, like the volume of medicine delivered, changes when the input, the stroke of the plunger, varies. See the green box representing the input and an orange lever representing the output. As the height of the green box changes, it causes the edge of the orange lever to move. This movement is the output. In a neutral design, the output responds directly to the input. If the input increases, the output increases proportionally, assuming the relationship between them is linear. This means any variation in the input is fully transferred to the output. But now, let's consider a robust design. In a robust design, the system is intentionally built to absorb or dampen variations in the input. So, when the height of the green box changes the same as before, the orange lever still moves, but not as much. The output is less sensitive to the input variation. The design doesn't eliminate variation entirely, but it minimizes its impact. The result is a more stable and predictable output, even when the input fluctuates. Now, let's go back to our syringe example. Which design is less sensitive to variation in the plunger stroke? Imagine the dose you need is 10 milliliter, and we want it accurate within half a milliliter to make sure you get the right amount. But here's the challenge. The person injecting isn't perfectly precise. They might vary by about 1 millimeter in the stroke of the plunger. So what happens then? Well, it all depends on the design of the syringe. Let's start with the short syringe and calculate the variation in its volume, approximating it as a cylinder, just like in the illustration. If we input the diameter and stroke length, along with their tolerances, into the RD8 platform, we can quickly estimate the variation in the dose you'll receive. First, let's look at the worst-case scenario. The dose could vary by plus or minus 0.77 milliliters. That's already outside our target of 0.5 milliliters. For a more realistic approach, we switch to a Monte Carlo analysis. The variation improves, but it's still greater than the required limit. This means the short syringe design is sensitive to input variation and cannot meet the accuracy requirements we set for the syringe design. Now, let's analyze the long syringe using the same approach. We input its diameter and stroke length into RD8, and again check the worst-case scenario. This time, the variation drops significantly compared to the short syringe. When we switch to Monte Carlo analysis, the variation is even smaller, well within our target of plus or minus 0.5 milliliters. That means the long syringe design is much less sensitive to input variation and meets the accuracy requirements. So, the choice does matter. A longer syringe design is more robust and delivers a more consistent dose. Now, compare this to the previous lever and box example. If the pivot point is close to the input, a small movement causes a big change in the displacement of the edge of the lever. But when the pivot point is further away, that same small movement creates a smaller displacement. That's sensitivity in action. The output changes dramatically depending on geometry of the mechanism. Just like with the syringe, the geometry of the design determines how much variation in your input translates into variation in the output. The short syringe acts like pushing close to the pivot. Tiny errors create big differences in dose. The long syringe, it's like pushing at the far end. Your input variation has much less impact. Let's highlight some best practices to reduce sensitivity in your next design. First, it's important to position rotational locks as far apart as possible. When these locks are spaced out, the system becomes less sensitive to angular deviations. In other words, the further apart they are, the smaller the angle error becomes, which helps maintain precision and stability in the output. Second, keep dimensions small whenever possible. Larger dimensions require larger tolerances, and larger tolerances introduce more variation. By designing with smaller dimensions, you naturally reduce the amount of variation that can occur, which contributes to a more predictable system. But what about springs? Let's look at these two examples. We have a short and stiff spring and a long and soft spring. For the same load requirement, which one of them will be less sensitive to variation? To answer this question, we created a jig that will allow us to test the influence of a variation in the pre-tension of the springs. Let's look at a video and see how it works. First, we compress the springs until the nominal target weight of 33 grams is reached. Now we increase the compression of both springs slightly, and look at that difference. The softer spring increases the weight to 40 grams, while the stiffer spring reaches 71 grams. It is clear that the short and stiff spring is more sensitive to variations in the spring compression. So, if you want to reduce the effect of the spring compression in the output of your designs, use longer and softer springs instead. Let's see another way to reduce sensitivity. Using the 3 boxes in a cradle as an example. Our goal: ensure a nominal gap between the cradle and the blue box, with a lower specification limit of 0. We can see that currently this requirement is not met. How can we improve it? Sure, we could tighten tolerances, but that would drive up manufacturing costs. Instead, let's think creatively. Right now, the tolerance chain has 4 parameters, adding variation. If we reduce the number of parameters, we shrink the chain and reduce variation. For example, redesigning with a longer purple box cuts the chain to 2 parameters. Even though the parameter now needs a bigger tolerance, the total variation is smaller than with 3 boxes, while keeping the same IT grades. So, remember to simplify and reduce the number of parameters in your tolerance analysis to avoid complexity and unnecessary variation.
Do you know the quality of your designs? We do.